Hello, today we are going to work on writing formulas for ionic compounds. So last lesson we showed the transfer of valence electrons from the cation, your positive ion, to the anion, or in other words, the metal transferring electrons to the nonmetal. Now we need to work on actually writing these formulas without the support of Lewis structures. So first we need to look at some naming things related to ionic compounds. The typical format for a name involves the metal ion being named first, followed by the anion. Now, one of the things with the anion is that they change the ending of the name so that it has an IDE ending. So if you are looking at names, you should be able to figure out at least the symbol of the first one because it's just the name of the element. And then if you're figuring out the symbol for the second name or for the second element, you need to look at the IDE ending and then look at that root and figure out what element looks closest to that on the periodic table. This one most looks like chlorine, so I know that's going to be my Cl. There is a proper way to write the formulas, and we do need to look at our charges, and I'll talk about that in a minute. When we're dealing with some types of elements that have unknown charges, so if I look at a compound like FeCl3, iron is a transition metal. If I'm given the name of my iron chloride compound, it will have a Roman numeral in the name, which will tell me the charge. If it doesn't have the Roman numeral in the name, I can use the charge of the anion, so chlorine we know has a 1- charge, and I can work backwards to figure out the charge of my iron ion. If I have 3 chlorines, each with a -1 charge, in total I have -3 on one side of my compound. In order to have an ionic compound, we discussed that the charges have to add up so that we have an overall neutral charge or a 0 charge. So if I have a -3 for my chlorine, it's because I've got 3 sets of -1, then I must have a +3 for my iron ion. If I have a +3, the name for something like that would be iron 3 chloride. They use Roman numerals to refer to the charge of the metal ion. They only use those Roman numerals when we're looking at transition metals. Transition metals are in this center section of our periodic table. Sometimes you'll also see some of these elements around here also have Roman numerals. Remember that anything to the left of my staircase is a metal, generally, and anything to the right we consider as a nonmetal. There are some exceptions to that, but for the most part, that is a true statement. The last thing that we have to pay attention to when we are writing formulas is that we are writing the smallest ratio possible. If you've balanced equations before, we know when we're balancing equations, we have to have a simplified ratio. Same goes with formulas. So if I had something like calcium oxide, Ca2O2 would simplify down to CaO. And I'll show you that in practice when we do some other examples later. When we left off last, we used our Lewis structures to show us how to transfer our electrons. One of the things I point out in my classes when I go over these problems is to look at your charges and compare it to the formula, which the numbers in the formula follow a certain pattern every time when we write the formula. You'll notice that magnesium had a +2 charge, but nitrogen is the one that gets a number 2 as the subscript. Nitrogen had a -3 charge, but magnesium gets a number 3 as a subscript. Remember that when we drew these, we ended up with 3 magnesium and 2 nitrogen. So as a result, the only way to balance those charges is to have opposite numbers. We end up switching these numbers when we write our formulas. The other thing you notice with the formulas is that we don't ever put the charges in the formulas, because the formulas represent subscripts, and the subscripts are your number of atoms. So we only look at whole numbers of atoms. You can't have a negative number of atoms, because that breaks our law of conservation of matter. So we're going to put this into action. Before we do that, I want to talk about Roman numerals real fast, because some people forget their Roman numerals. Here are the Roman numerals 1 through 10. You do need to be able to decode these. You should know them, memorize them. If you don't know them, you need to know them. One of the common issues I always see is people switch up these two for whatever reason, the 4 and the 5. All of those get switched up a lot. Just make sure you've got your right numbers for when you decode, because that's going to be related to your charge. Speaking of charges, when we are looking at the periodic table, we can figure out our charges based off of their location for just about everything except for the transition metals. We know that column 1A has 1 valence electron. If I have 1 valence electron, I am more likely to lose that 1 valence electron. When I lose a valence electron, I end up with a positive charge. So everything in my first column is +1. In column 2A, I can lose 2 valence electrons. I end up with a +2. So everything in that column is a +2. These transition metals, like we said, are going to be given to us by the Roman numeral in the name. So we use Roman numeral for charge for those. And then the nonmetals, we know 0 for my noble gases, -1, -2, -3. Carbon and silicon tend to be -4. These ones down here sometimes have a +4 charge, but they can also have a +2 charge and some other types of oxidation states that you might not see. And then we know aluminum and boron have a +3 charge. The transition metals, you're going to use a common ion sheet for these. We have a reference sheet. So if you aren't given a Roman numeral, you can at least look up the different types of ions. Things like iron can have multiple charges, +2, +3. Nickel, I've seen +1, +2, +3. Copper, I see +1, +2. Chromium, I've seen a +3. I think I've seen a +6 or a 7. They're all kind of all over the place when we're looking at those. So you need to look at those common ion sheets for those. All right, so let's put this into practice. When you are looking at the names, you need to first write your elements. Let's decode. Lithium is easy. We just find our lithium symbol. It's Li. Here we got to look at the word oxide. Remember that IDE ending is in play here. So you're not going to see IDE endings in the periodic table. You just have to look for the closest element. What would be the closest element to oxide? Oxygen. We look at oxygen here. We've got Li and O. That's my first step. You could do that as your first step for these other ones here. We've got chromium is Cr, chloride is chlorine, Cl, Sr is for strontium, and then oxygen is O. And then you need to look up your charges. If I look at the periodic table, my charge for lithium is a +1. My charge for oxygen is a -2. Remember, if I add my charges together, they should balance out to 0. In this case, it does not, so I need to switch my numbers. This is what we were talking about on the Lewis structure slide. When you switch the numbers, we call it the crisscross. The 1 that was with lithium comes down here. The 2 that was with oxygen comes down after lithium. And we end up with this formula, Li2O1. Now we know that we never really need to write the 1 because it's implied, so the formula would just be Li2O. If I go back and draw the ions for these, what this is really saying is I have two lithium ions, each with a +1 charge, and I've got one oxygen ion with a -2 charge. If I add those up, 1 + 1 plus a -2, it sure does balance out to 0. Now, this is not something I'm going to ask you to do, but it is a way to check your work if you need to check your work. All I need to see is your final formula. The other thing that's common, people tend to write their charges up here and then just leave them there after they've done their crisscross. You do not need to write your charges above the elements. The proper way to write a formula is to leave the charges off. Second one, let's apply that Roman numeral rule. Here's my Roman numeral 3. That represents my charge of 3. The charge in the Roman numeral always refers to the metal. So chromium has a +3, chlorine has a -1. If I switch my numbers, chromium would get a 1, but we don't write the 1, and chlorine gets a 3. Our final formula is CrCl3. Strontium would have a +2, oxide would have a -2. This one is interesting because if you try to switch your numbers, hey, they're the same. If you go back to your notes, remember we talked about this rule here, simplifying the subscripts when possible. 2 and 2 can simplify down to 1 and 1. So we're going to do that. If we simplify down to 1 and 1, sure enough, everything's balanced. But remember, you don't need to write your 1s. So the formula was actually correct when we wrote it the first time. It's just SRO. That is writing ionic formulas for binary ionic compounds. The word binary means 2. So binary ionic compounds just refer to compounds with 2 elements in them, 1 metal and 1 nonmetal. Next time we will address polyatomic ions, which are ions that have more than 1 element in them, and how those things ionically bond with other metals. Those kinds of compounds end up having 3 or more elements in them, and we're going to look at how they bond. That is all for today. See you soon.